Good morning, everybody. We will talk about Java bytecode compile time optimization, specifically focusing on Stream API, which was introduced in Java 8 together with the lambda expressions in 2014. Look at the snippet on the left. It's pretty traditional classic way of processing array of numbers in mostly any object-oriented, or not even object-oriented programming languages. On the right side, you see an alternative way of doing exactly the same, but via streams or Stream API in Java. The way it looks on the right is more convenient for programmers because it clearly separates the concerns. Every step, every operation of the stream is doing one thing. First, we filter, then we map, and finally, we summarize. Here on the left, we do all together, and it's less expressive and less declarative. However, there is a problem with that. Every lambda expression here is internally an object, which is supposed to be called by Java runtime through a virtual call. And that leads to performance degradation, which was understood by Java programmers almost immediately after lambda expressions were introduced together with Stream APIs. Developers of open source products and large frameworks were concerned about performance, and some of them even openly declared their unwillingness to use Stream API because of performance problems. 6 years ago, a solution was introduced by a group of researchers who suggested to create a bytecode-to-bytecode stream unroller. The principle was simple. Just take the Stream API and after it's compiled to bytecode, convert it to a loop, convert it to an imperative alternative, which we saw on the previous slide. And it was a good solution because it demonstrated performance gain on a number of benchmarks, obviously making streams more useful and more interesting for programmers because of the performance optimization. We tried to reproduce their results, and we did that. But the problem was that the modern versions of Java virtual machines, they somehow know how to run Stream APIs as fast as loops. So what was the problem 6 years ago is not a problem anymore. If you look at the numbers here, then the first column, the first group of columns are about Java virtual machines of earlier versions, which were available when Java lambda expressions were introduced. And this right group of columns are about current versions of them. The numbers on the ratio column is the correlation between the time taken by the stream pipeline comparing or divided by the time taken of a loop, which is doing exactly the same. On earlier versions like 8 or 11, the numbers are obviously not in favor of Stream API. Loops are faster, to put it simple. But on modern versions like version 24 and 26 of Java Virtual Machine of the same vendor, we see that loops are actually slower than stream pipelines. That sounds like a surprise, but it is what we discovered during our research. But this only affects short pipelines, which are optimized internally by Java virtual machines somehow inside their runtime machinery. On longer pipelines, this is not what it looks, this is not what we see. If you take a look at this so-called megamorphic benchmark, which was used by the previous study, the baseline, which I already mentioned, this megamorphic pipeline still works about 10 times slower in form of a stream pipeline comparing to a similar algorithm if it's implemented in form of a loop. Even on Graal VM, which is the most advanced instrument for optimization of Java code in runtime. This pipeline, this benchmark is still about 10 times slower if it's in the form of a stream pipeline. So what we decided to try to do with that, we found out that in Java 16, just a few years ago, a new operation was introduced, which is called mapMulti. mapMulti is something that may be used instead of some previously existing stream operations, like map and filter. If you look at this pipeline, which does basically two simple things, first it's mapping, then it's mapping again. Then this pipeline can be replaced by one operation. We can join these two adjacent operations into one. Instead of having map and map, we can have mapMulti. mapMulti will do exactly the same, and it will have just one lambda expression. So by joining two adjacent operations, we can have less Java expressions. If we join two of them, then we can join three of them and four of them and so on and so forth. And we can join 7 of them, thus potentially reducing the time which is necessary to run a long pipeline. That was our hypothesis. So we asked 2 research questions. First one, can we join 2 operations like map and filter together and gain some performance and have some performance gains which are similar to what stream unrolling can provide? And the second question, whether we can safely do that. Can we take existing stream pipelines, join these operations together, fuse them, like reduce the size of their pipelines, and still have the code which has no bugs and still runs as it was running before? To answer these questions, we build our own optimization pipeline. It works like this. We take binary bytecode files, .class files. Then we transform them to XML format, which is necessary for our optimization. From this XML format, we go to phi expressions, which are phi calculus expressions. I will demonstrate in a few minutes. Then we convert these phi expressions, which are representing the original bytecode, to a different phi expression through a number of optimizations in form of rewriting rules. We get to a new phi expression, and then from this expression we go back to XML format, and from XML we go back to .class file, which is a bytecode file. This whole pipeline is invisible, undetectable, and transparent to developers of Java code. They just compile their code as before, they get bytecode files, then our pipeline goes, it transforms bytecode to bytecode, and the code just runs. So what is a phi expression? Phi calculus expression is a representation, formal representation of potentially any Java code. On the left you see the Java code, which is before compilation. Then this is the compiled bytecode, as it is represented by Java P, printer of the bytecode. And on the right side, this is the block of the fragment of phi expression, which may resemble S expressions or JSON code. Like the most primitive way of looking at it, it's a JSON format which represents a complex bytecode structure. This one is less complex and more suitable for rewriting rules. It's easier to manipulate with it for our optimizing and rewriting rules. So what are these rewriting rules? We can think about them as a more advanced form of, let's say, regular expressions. On the left side, you see a pattern. On the right side, it's a replacement. The pattern says what particular part of the expression needs to be replaced with what. And then these parts, like B1 and B2, they left untouched. We don't care what's in the B1 and what's in the B2. We only care to match this particular part of the expression and replace it with a different part of the expression. That's all. We have 44 rules like that. They do the transformations of our phi expression like I showed before. And this is our pipeline, how we deal with the opcodes related to map and filter. If you are familiar with the bytecode for Java, you may understand these opcodes. We take two of them, invoke dynamic, invoke interface. If they stay together, we understand that they are relevant to the stream pipeline. We fuse them, we lift them to map, so-called pragma map, and these two we lift to filter map. Filter pragma, sorry. Pragma is our own synthetic opcode. It doesn't exist in real Java bytecode. It's what we invented. This is our own pragma. Then these two pragmas, we transform to a uniform distilled pragma so that they look similar on the interface. And finally, we have the fusion step. If they are similar, if they are uniform, then we can join them by just concatenating the bytecode to bytecode. Each of these pragmas, they contain the bytecode which was originally there related to lambda static functions. We concatenate it here, and then we lower it to mapMulti, and then we lower it to, again, a pair of opcodes. That's the entire pipeline in a primitive representation. What we get after that, we start from 4 opcodes and we finish with 2 opcodes. That's the fusion process of 2 adjacent map and filter operations of a stream pipeline. So what we got? Speaking about numbers, take a look at the right part of the column because it is the results of testing on the latest or one of the latest versions of Java Virtual Machine. We use Zulu 23. On the left column, you see the results which we receive from the baseline, the Streamliner, which was created 6 years ago. They do unrolling, and this is the results of us. We do stream fusion. Let's go benchmark by benchmark. These are the benchmark which were introduced by them. Actually, they were introduced before them, but they were using these benchmarks, so we decided to use the same. The first 2 benchmarks, they outperform us. They optimize better than us because in this case, they also optimize terminal operations, which are all match and count. We don't optimize terminal operations just because the nature of our optimization. So we lose here. We are better than Java Virtual Machine. We of course gain some performance. We're faster. Our optimization makes sense, but their optimization is way more effective on these benchmarks. On the next 2 benchmarks, which are filter count and filter map count, they actually degrade the performance. So their optimization from a stream pipeline to a loop makes the code work slower. We don't do that. We keep the performance at the same level. We don't optimize, but we don't degrade. On the next 2 benchmarks, which are megamorphic filters and maps, previously mentioned, we optimize as good as they are. They achieve 20x optimization result. We achieve the same. So we show that stream fusion with the help of mapMulti can be as good as stream unrolling on the same benchmark. And then the 3 other benchmarks, they don't achieve anything, we don't achieve anything as well. And the second part of our study was how safe the optimization is. Apparently it's pretty safe in a subjective test. We applied our optimization on Apache Kafka bytecode, which contains about 1 million lines of Java code and 140,000 lines of Scala code. We compiled all that, and then we ran about 32,000 unit tests on this project, and none of these tests broke after our bytecode modifications, which gave us a good signal that the optimizations may work on large code bases. Interesting to notice that the time it took for our tool to optimize their bytecode was about 40% plus on top of the compile time, which is a significant increase on compile time, which may be an important negative factor for large projects, which we will think about this in future studies, how to reduce this time. So let me finish on 3 interesting outtakes from this study. First, we can claim that the stream fusion via mapMulti can be as effective on some benchmarks as stream unrolling. Second, we say that phi calculus did a good job for us, helped us to represent bytecode in a declarative way as expressions, and then allow us to apply rewriting rules. This instrument, this calculus, may be used for other optimizations in other projects, in other studies, and we are ready to share more details about that if you're interested. And finally, interesting to say that we only worked with 2 stream operations, map and filter. There are many more of them in the Stream API. Well, many more means like 20 more. How to deal with these other operations, it's a question for future studies, which we're doing right now. And let me disclose that we already managed to find a way how to optimize and fuse most of them as well, not only map and filter. But in this study, which I just presented to you, it's only about map and filter, and the results you just saw. So that's it, ready to answer your questions.
Okay, yeah, is our speaker online, I guess? Can our speaker hear from the audience? So can the speaker hear us? Can the speaker confirm? Is he muted? It looks like our signal is transmitting to the speaker side. Okay, I guess we can reserve our questions and ask them in the channel. So, is the speaker online now? Can you talk to us, Yegor? Yeah, okay. This happens, and this is a real hard problem the computer science should solve, not that. Okay, so let's just post our questions to the channel, and we have a channel right in the Discord. Okay, so I guess we can switch to the next speaker. So our next speaker, Rajpal, is a senior software engineer at Google, working on